Yes, so I hope my screen is visible. Okay, so hello everyone. This is lecture 20 on discrete mathematics, and this will be our last lecture. So today we will complete this subject. So even if we need 15 or 30 minutes more, I will take that. Okay, and I will complete it. Okay, so planar graph topic we are studying, and we have to see whether this graph is planar or not. That is very simple. Okay, so I think you have got it. What we will do? So we will simply shift. Okay, let me take this. So yeah, so that was creating problem for us. So what we will say, we will take it from outside, that's it. So this is planar, 100% planar, and this is planar. Yes, this is for sure planar. Why? Because we have a vertex here. Since we have vertex here, so we will not say that they are crossing each other like this is a you can say circle, or you can imagine it just like a vertex. So here these edges are coming, so where they are crossing, they are not crossing. So do not worry about it. It is a planar graph for sure. Okay, this is planar for sure. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so now we are going to study few standard examples. Cn, that is for sure planar. Kn, complete graph. So complete graph till 4 vertices, that is planar. But K5 and beyond K5, they all are non-planar. Okay, why they are non-planar, I think you already know. I have told you in the previous class also that if a graph contain K5 or K33 as subgraph, then it is not planar. Okay, so I have told you. So clearly all of them will be non-planar. Why? Because K6 will contain K5, K7 will contain K5, and so on. I think you remember. See, this is K3. How we have built K4? So we will take K3, and then we will take a new vertex, and then we will join all of them. So that's how we get K4. So directly indirectly K4 contain K3. Now what about K5? K5 will contain this K4. Why? Because I will join all this. Now K5 is non-planar. So if I make a K6, K7 and so on, every you can say graph will contain this. So obviously they will not be planar. So all of them are non-planar. But is null graph of n vertices? For sure planar. Okay, there is no edge. Wheel graph 100% planar, no need to worry. Okay, because we have vertex here, so vertex will not create problem for us. Okay, since every cycle graph is planar, so obviously every wheel graph will also be planar, because wheel graph means we will just make a vertex in between and we will try to join all the edges. Okay, like we have spokes, I think you already know na. This is your wheel graph. Okay, so W5 W6, how W6 will look like, we will make a pentagon. This is planar, so we will make another vertex, and now I will join all this. So planar only, no problem. Okay, Kmn, m is less than 3 or n is less than 3. Okay, only then it will be planar, otherwise it will not be planar. Why? Because if m and n both are greater than or equal to 3, they will definitely contain K3 as subgraph. That will create problem for us. Okay, yeah, and if you want an intuitive idea, let me give you that intuitive idea also, so that you get more clarity. So for example, I have say K2, and here no matter how many vertices you want to make, you can make it. So I will join all this. So no, okay, so planarity is still there because no edge is crossing over this. You might think that this will create problem because this is crossing. No problem, na. You take it from outside like this. Okay, so now you take it here, you take it here, you take it here, and you take it here like this. Okay, so no edge is crossing, you can make it. I think it is very easy task. So no edge is creating problem. Now the moment you make a third vertex, that will create problem, because now we have closed this path. Okay, so it will we will take it outside, and the moment we take outside, it will cross over and will create problem for us. Okay, so that's why when m is less than 3 or n is less than 3, it will be 100% planar. So or na, I'm saying or, that means I can take K200, like K200, this will be 100% planar graph. Okay, or K102, this will be planar, or K1500, this will be planar for sure. But if m and n both are greater than or equal to 3, that will create problem for us. So I hope you have got the point. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, Peterson graph. Peterson graph, this came in GATE 2022. You can Google it out why it is non-planar. Peterson graph is non-planar. Why it is non-planar? you will Google it out, and in Wikipedia you will find a very beautiful animation showing it. So if I try to make it, it will simply waste our time. You can see the animation, you will get the clarity that why it is non-planar. Okay, so I'm not digging deep into that, and this software is not supporting animation, otherwise I have shown you here itself. Okay, so no need to worry, it is you just have to remember it is non-planar, and this question has been asked in GATE 2022. I have told you many times, Peterson graph is very very important. Okay, many questions have been asked from Peterson graph. So you have to remember all the properties of Peterson graph, like it is three regular. Okay, it was not Hamiltonian. Okay, three regular, it was not Hamiltonian. Okay, and since it is three regular, odd degree na, so it will not be Euler. Like this, you have to remember these properties, very very important graph. Okay, take snapshot, I will jump to the next slide. Yeah, and one more thing, let me write it. No, I have written here itself, non-planar. Yeah, so let me jump to the next slide. So which of following is non-planar? K4 100% planar. Why it is planar? Because it is not containing K5 or K33 as subgraph. Okay, K20 not planar. Okay, so yeah, which is they are saying not planar na, so obviously it is not the option because it is planar. This is not planar, so it is the option. C100 100% it is planar, or 510 obviously it is planar. Okay, so B is correct. Take snapshot, I will jump to the next slide. Okay, so which of the following is not planar? K200. So K200 clearly it is planar na. Why it is planar? Because I have told you just now, we have only two vertices here. Okay, so here 100, so everywhere it will be connected, but from here you can take it from outside and so on. It is planar. We want not planar. K300, no, it is not planar graph, so this will be our answer. Okay, K101, yes, it will be planar, 100% sure, so it is not the answer. And K102, yeah, no, it is not the answer. So I think you have got it. B option is correct. Any doubt here?
No, sir.
Okay, take snapshot, I will jump to the next slide.
No, sir.
Okay, so now we are going to study Kuratowski's theorem. I have told you in the previous lecture that Kuratowski's theorem is roughly, I have told you na, that K5 or K33 is present in the graph or it is subgraph. Roughly I have told you, but now I am showing you the correct definition, and this is very very important definition, as it is definition has been asked in GATE many times. So what the definition is saying, a graph G is planar if and only if it does not have any subgraph homeomorphic to K5 or K33. What is homeomorphic? I will tell you this thing now. Okay, homeomorphic is very important term. Okay, so before studying homeomorphic, we have to study some basic terminology. ESD. ESD is elementary subdivision. Elementary subdivision means putting vertex on an edge is called elementary subdivision. On an edge, single edge. On a single edge, if you put vertex, that is elementary subdivision. For example, here, this is a graph, and on this edge you have introduced a vertex, so it is one elementary subdivision. Are you getting it? On an edge, if you take vertices, that is elementary subdivision. For example, this is an edge of a graph. Some graph is there, this is the edge. Now you put here one vertex, that is elementary subdivision. Okay, that means you have subdivided. Why I am calling it as elementary subdivision? Because you have divided this edge into two parts. Okay, this is one edge, this is one edge. Okay, so this is one elementary subdivision, and on an edge, single edge. Take snapshot, I will jump to the next slide.
Done, sir.
Okay, so here how many subdivision we have done? So here we have introduced one vertex, here we have introduced one vertex, so we have done two elementary subdivisions. Okay, so I think you can see it, and see here how many elementary subdivisions are done here. I have put vertex here, so obviously it is not elementary subdivision. This is wrong. Why? Because I have put vertex on two edges. On two edges it is not allowed. Now I have told you on one edge.
One edge.
Okay, yeah, so we have here two edges, so it is not elementary subdivision. This is okay. Take snapshot, I will jump to the next slide. Okay.
Done, sir.
Okay, so next is elementary subdivision, divide one edge into two edges. I think I have told you this thing. So do any number of elementary subdivision, we get homomorphic image of the graph. That is homomorphic image. So what is homomorphic image? Do any number of elementary subdivision. You do one elementary subdivision, 2, 3, 4, 5, whatever you want, you can take. Even zero elementary subdivision also you can take. No need to worry. Okay, so 0, 1, 2, 3, any number of elementary subdivisions you have to do. An elementary subdivision means you can put vertices on an edge. That is okay. Now simply we can say that add any number of vertices to an existing edge, make it homomorphic to actual graph. Okay, so for example, this is a graph given to you, so you can homomorphic image will be H, like this we will write. So homomorphic image will be You introduce here vertex, here. No need to worry. Whatever number vertices you want, you can take. It will be homomorphic image, no problem. Okay. So see this. Now I have written here. Hence, actual theorem is bit complicated. Now that's why I have shown you the simpler version in the previous lecture. That roughly you say subgraph. Okay. So, but actual theorem is a bit complicated. That ways K5 or K33 may not.
In this conference.
Okay, so I hope some problem. Let me see this. Okay, yeah. So where I was, so hence actual theorem is bit complicated. That is K5 or K33 may not be present directly in G. Rather, even if their homomorphic image is present in G, it won't be a planar. Okay, so graph will not be planar even if its homomorphic image is present. Okay, so no need to say that K5 or K33 is directly present. No, it might not be directly present. Okay, so its homomorphic image may be present. Okay, so I hope you have got the point. So take snapshot. I will jump to the next slide. Done.
Yes, sir.
Okay, so yeah. So isomorphic implies homomorphic. That is one way theorem. Okay, so if we have isomorphic image, then obviously it will be homomorphic. That is very simple. See this. This is a graph given to us. Say A, B, C, D. So now you can twist it like you make it this way. Okay, so A, D, C, B, like this. So they are isomorphic and clearly they are homomorphic only, because here we have done zero elementary subdivision, no problem at all. Okay, so it will not create problem for us. So if isomorphic, it is homomorphic, it is one way. So if homomorphic, then isomorphic, no. For example, this is the graph and this is the graph, and here I have introduced one vertex. So A, B, C, D and E. Here A, B, C, D. Are they isomorphic? Never, because there we have 4 vertices and here we have 5 vertices. Not at all, but they are homomorphic. Okay, so converse is not true. So this is correct, but this is not. Okay, yeah, take snapshot. I will jump to the next slide. If you have any doubt, please ask me.
No, sir.
Yeah, should I jump to the next slide?
Yes, sir.
Okay, so graph is non-planar if and only if it contains homomorphic image of K5 or K33 as subgraph. Yes, this is correct. This is gate question. It is isomorphic to K5 K33. No, if and only if they are saying na both ways. Those actual theorem, they are asking actual Kuratowski's theorem. So it is isomorphic to K5 K33. No. Okay, because there might be many graphs. For example, if you take like this, let me take it. Okay, so let me make the graph. Okay, I have made this graph. So this is not isomorphic to K5 or K33, and still it is non-planar. Okay, and it contains K5 or K33 as subgraph. Yes, so this graph is containing K5 or K33 as subgraph, but there might be some other graphs. For example, I introduce here vertex, here vertex, here vertex. So there is no subgraph. K33 is or K5 is not subgraph of this graph, but still it is but still it is non-planar. Why? Because homomorphism. So this is correct. That's what is correct. So C is wrong. It contains homomorphic image of K5 and K33 as subgraph. So in gate exam you will find this type of question and it will confuse you. Here we have or is correct. Here we have introduced and. No, and is not correct. We do not need both. We need only one. Okay, so A is correct. Take snapshot. I will jump to the next slide. Done. So I think you are not audible.
Sir, you can hear me?
Yeah.
I'm done with the screenshot, sir.
Okay. Okay. Yes, so number of vertices and edges in smallest non-planar graph in terms of vertices and edges respectively. So number of vertices is smallest non-planar graph. So I think I have told you K5 was non-planar smallest and K33. So in terms of vertices 5. In terms of edges, K33 was containing 9 edges and K5 was containing 10 edges. So number of vertices and edges in smallest non-planar graph in terms of vertices and edges. Vertices 5 and edges 9. Any doubt?
No, sir. We discussed
Okay.
this yesterday also.
Yeah. Good. Yes. So let me jump to the next slide. Okay, so next is Euler formula. Okay, so Euler formula for connected planar graph. This is important. Many times question has been asked. So what it is saying, R is equal to E minus N plus 2. R is the number of regions, E is the number of edges, and N is the number of vertices. R is equal to E minus N plus 2. And see this, it is for connected planar graph. Connected. Okay, so that means one piece. So it is true for any connected planar graph, that is simple, multi, pseudo. It can be any type of graph. It will be true. So verification purpose I have done here. I am not going into proof and all. So I have just shown you this verification purpose. You can count these things. So here number of regions are 5, 1, 2, 3, 4, and 5. Fifth region is the open region, outside region. Edges are 13, you can count. Vertices are 10, you can count yourself. R is equal to E minus N plus 2. So you can count this. This is the correct. Similarly here also regions are 3, 1, 2, and 3. Third region is the outside region, that is open region. Number of edges are 8, vertices are 7. So finally we have got it. Yeah, so I think you have got the point. If you have doubt, you can ask me. Otherwise, I will jump to the next slide.
Yes, sir.
Okay. So next is Euler formula for planar graph. So now here connected word is missing. Connected word is missing. So connected is missing means it can be disconnected also. Disconnected means now connected component will come into the picture. Because it is disconnected, so connected component will be more than one. Okay, so connected component will now come into the picture. So what it is saying, okay, just a second. Yeah, so Euler formula for planar graph. So connected, that means connected is not there, connected is missing. So we will say connected components are there. Okay, so what is the formula? R is equal to E minus N plus 2 was there. Na? So now here we have K plus 1. So you can put K is equal to 1. If graph is connected, K is equal to 1. So our formula will be R is equal to E minus N plus 2 only, which we have studied in the previous slide. Okay, so 2 was, so this is more general formula. So if we have connected graph, so we will say that K will be equal to 1. So R is equal to E minus N plus 2 and so on. So we say same, R number of the region, number of edges, number of vertices, and K is the number of connected components. For verification purpose, I have shown you this graph. So this graph is having connected components 4, edges are 17, N is 16. So you can put the formula and get the answer. Okay, so it is true for any graph, simple, multi, or pseudo, any graph. Okay, yeah, take snapshot. I will jump to the next slide.
That's all.
Okay, and this is very important. Many times question have been asked. So try to remember this formula. By putting this formula only, formula based question have been asked in GATE. That is the beauty of this formula. Direct formula. Apply formula and get the answer. Take snapshot. Okay, yeah. So okay. So a planar graph with order 10, size 5, and 13 component, divide the plane into how many regions? This type of question have been asked in GATE. So order 10 means number of vertices are 10. Size 15 means number of edges are 15. Connected components are 3. So R is equal to E minus N plus K plus 1. So edges are 15 minus 10 plus components are 3 plus 1. So you can calculate it. What will be your answer? 1. So region is 1 only. Any doubt?
No, sir.
Okay.
Correct, sir.
Yeah. So let me jump to the next slide. So how many closed regions are there in the previous question? Okay. So I have done some mistake. Yeah. E minus N plus K plus 1. So E number of edges are 15. E minus N plus K plus 1. Oh yeah. Calculation mistake. So 15 minus 10 is 5. 5 plus 3. 8 or 9 is the answer. है ना 9 आएगा ना 9 is the answer. So that's why I when I see the next question then I go to know I think there is some mistake. So region is 9, total number of regions are 9, and what they are saying closed region will be -1. So 9 minus 1, that is 8. So you can check this out. So in this graph, so number of regions were 1, 2, 3, 4, 5, and 6. Total 6 regions were there. Why 6 regions were there? 1, 2, 3, 4, 5, and 6th was the open region. So now I'm saying that you just want to remove that open region. So obviously -1 you will do. So answer is 8. Any doubt?
No, sir.
Okay. So let me jump to the next slide. So theorem in a connected planar, in a connected simple, see this simple planar graph, 2 is greater than equal to 3R. Okay, so twice the number of edges is greater than equal to 3 times the region. I'm not going into the proof of it. I will just tell you that R is equal to E minus N plus 2. From this formula we will get it. I'm not deriving it just to save the time. Okay, so you should remember this, and many gate questions can be solved from this formula only. So 2E is greater than or equal to 3R. Take snapshot. I will jump to the next slide.
Done, sir.
Done? Okay.
Yes.
So in a connected simple planar graph, same. Previous also, connected simple planar graph. You have to remember this thing. Connected simple planar graph. Here also connected simple planar graph. What is E less than or equal to 3 and minus 6? That is also very simple. So R is equal to E minus N plus 2. This is the formula. And I will put this. 2 is greater than or equal to 3R. So I will put here, if I multiply everything by 2, or you multiply by 3. So 3R is equal to 3E minus 3N plus 2. So what we have said here, 2E is greater than or equal to 3R. So if I put here 2E, that will be greater than or equal to 3E minus 3N plus 2. Okay, so
Should get multiplied.
yeah, please come again.
3n plus 2. Why not we multiply 2 also with 3?
Oh, sorry. 6. Here also 6. Okay, yeah, so E will be less than or equal to 3N minus 6. This is the formula which we have derived. I think you have got it now. Okay, so take snapshot. I will jump to the next slide. So this is very, very important. Okay, so next is a connected simple planar graph of order 10. E can be at most. So I think you have got it. So they are trying to find relationship between edges and vertices. So what we have derived here, E is less than or equal to 3N minus 6. So these type of question have been asked in GATE. Why? Because nobody will be able to remember this type of formula. You will be able to remember this formula, and you will be able to remember this thing. From that you can derive in GATE exam what was this relationship between edges and vertices, and from that you can get the answer. So 3 into 10 minus 6. So E less than or equal to 24. So at most 24 answer. Any doubt?
No, sir.
Okay, so let me jump to the next slide. So theorem, in a connected planar graph, delta will be less than or equal to 5. So minimum degree, delta was minimum degree. So minimum degree in a graph should be less than or equal to 5. Okay, so how we can prove it? So this is very simple. So I think you already know delta is less than or equal to 2E by N is less than or equal to capital delta. Okay, so now 2E by N, here we have delta theorem. We have solved this in previous lectures only. Yeah, so delta will be less than or equal to 2E by N. And what is the relationship between E and N? We have told you E is less than or equal to 3N minus 6. So 3N minus 6 divided by N. So delta will be less than or equal to 3 minus 6 by N. Okay, yeah, so what we have, okay, so 2E was there, na? Yeah, so 2E, so I have to multiply it by 2 also. 2 into 3N minus 6. So it will be 3 to the 6N by N minus, okay, let me do it. I actually I want to save time because I have to complete many topics, but it is getting late and late. No problem. I will do it properly. So delta is less than or equal to 2E by N floor function. I think you already know this thing. 2E by N floor function less than or equal to delta. Delta theorem was this only. So I will say delta is less than or equal to 2 into E is less than or equal to what? 3N minus 6. So 3N minus 6 divided by N. So and floor function. So delta will be less than or equal to 6N by N minus 12 by N. Okay, yeah, so here N and N are gone. So if I take N to be very, very large, because for general graph I am saying, so we can consider it as a very small number, and 6 minus something floor function, it will be 5 only. Okay, we will get something in point, so it will be less than or equal to 5. Okay, so upper limit I have to calculate. Any doubt here? Please let me know, otherwise I will jump to the next slide. Done?
Done, sir.
Okay, So next, now we're going to start tree topic. So tree you have studied in data structure algorithm, so we will not dig it deep into it. I will just give you a small overview. So related to graph theory only. So connected and acyclic graph is known as tree. I think you already know it should be connected and it should be acyclic. Okay, so connected and acyclic directly means minimally connected. Minimally connected means even if I delete one of the edge, then it will not be a tree or it will be disconnected. Okay, yeah, so this is a tree. Yes. Is this a tree? No, because there is a cycle. Is this a tree? Yes. This is a tree. Yes. This is a tree. Yes. This is a tree. Yes. Okay, so all are tree except this one. One piece and open structure. Okay, this is the basic terminology, not informal definition. So it should be in one piece and it should be open structure. Take snapshot. I will jump to the next slide. Done. Okay. Yeah. So now we are going to study few properties of tree. So a tree with two or more vertices is bipartite. I think you have guessed it because bipartite means no odd length cycle. Now there is no cycle at all. Then obviously there is no odd length cycle. So it will be bipartite. Chromatic number of every non-trivial tree is true. Two. Trivial tree is this only. Okay, so its chromatic number will be 1. But for non-trivial it will be 2. Why? Because it is bipartite. Since it is bipartite, so chromatic number will be 2. We have discussed it in previous classes also, and anyway today also I will discuss it, so don't worry if you are not able to remember it. Today we will also discuss it. Okay, so every bipartite graph chromatic number is 2. Okay, now every edge in a tree is cut edge and every non-leaf node in tree is cut vertex. I have told you in the previous lecture only. In a tree with n greater than equal to 2, if we put an edge between any two vertices, it will create exactly one cycle, and this cycle is called fundamental cycle. What this point is saying, for example, I have constructed this tree like this. So what I am saying is, if you put an edge between any two vertices, it will create exactly one cycle. For example, you take this, you put an edge, so obviously this is a parallel edge, no problem, but we have got a cycle. Similarly, if you put edge between them, we have got a cycle. Similarly, if you put edge here, we have got a cycle. If you put edge between them, we have got a cycle. That's it. So this is the basic meaning here. So in a tree with n greater than equal to 2, if you put an edge between any two vertices, it will create a cycle. It will create exactly one cycle, and this cycle is called fundamental cycle. Now tree of n vertices will have n C2 fundamental cycle. That is very obvious. If we have n vertices, I have told you now, you can put edge between any two vertices. So any two vertices means from n you pick any two, obviously NC2. So it will be NC2 fundamental cycle. Take snapshot. I will jump to the next slide.
Yes, sir. Done.
Okay. Okay, so tree of n vertices has n minus 1 edges. Obvious, you already know. Tree is minimally connected, we already know. For all xy belong to v, there exists exactly one path between x and y. That is also property of tree. If you want me to prove, I can prove it. Otherwise, I think in data structure you have studied it. So for example, from A to C, there is only one path, exactly one path. Two path means there is a cycle. Na? If we have two paths, that means there is a cycle. For example, like this. So A to C, we have edge, we have a path, or from A to C, we have another path like this. So that means we have a cycle. Okay, since there is no cycle, so exactly one path between every two pair of vertices.
Yes.
Yeah, take snapshot. I will jump to the next slide.
Done.
Okay. So counting graphs. Counting graph is very important. Many times question have been asked. So try to focus here. Graph is of two type: labeled and unlabeled. Okay. More important is labeled, because unlabeled questions are, you can say, it is on difficult side. We have to do it manual calculation. So manually you have to count. Okay. That's why unlabeled are. But no doubt questions have been asked. So do not say that question have been not asked. It many times it has been asked. So we have to study both of them. Labeled are important. Okay. Labeled, we have formulas and so on. Okay. So the very first question is, how many simple labeled graphs are possible with n vertices and e edges? So see this. If we have n vertices, so how many maximum edges are possible? N C2 edges are possible. So n C2 edges are possible in complete graph, na? I think you already know, because you pick any pair of vertices, you should have an edge. So from MC2 edges, you want to choose E edges only. So CE, that is my answer. Yes, please let me know if you have any doubt.
Got it.
Okay, okay. So take snapshot. I will jump to the next slide.
Done, sir.
Okay. So how many simple labeled graphs with 5 vertices and 6 edges? So 5 vertices means 5 C2 edges are total. That means 5 C2 is 10. So now from 10 you can pick any 6 edges. So 10C6 or 5C2 C6, one and the same thing. 5C2 C6, or you can say 10C6, or that is nothing but 10C4. So you can calculate it 10 into 9 into 8 into 7 divided by 4 into 3 into 2 into 1. Okay, so you can find it out. This is gone. So 3 3s are 9. So 210 is the answer. 210 are possible. Take snapshot. I will jump to the next slide.
Done, sir.
How many simple label graph with 5 vertices and at least 6 edges? So it will be a bit lengthy question. At least 6 edges, na? So 5C2 or 5C2 is nothing but your 10. So from 10 you want to pick at least 6. So 10C6 plus 10C7 plus 10C8 plus 10C9 plus 10C10. This is my answer. Okay, take snapshot.
Done, sir.
Okay, so next is how many simple label graph with 5 vertices and at most 6 edges. At most 6 edges means, so you will start from here. Let me copy it just to save the time. So what I will say here, I will say here, so 10C0, 10C1, 10C2, 10C3, 10C4 plus 10C5 plus 10C6. And why we have got 10? Because 5C2 is 10. Take snapshot. I will jump to the next slide. Done? Okay, so how many simple labeled graphs are possible with n vertices? That is a good question. Simple labeled graphs are possible with n vertices. So now they are not saying about edges. So you can take any number of edges. So what you will say, NC2 edges total, maximum NC2 edges are possible. So from these you choose 0 edge, or from these you choose 1 edge, or from these you choose 2 edges dot 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 up to NC2C NC2. So take NC2 as x. So what you will say, XC0 plus XC1 plus XC2 dot 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 XCX. So that is nothing but 2 power x. And what is x? NC2. So 2 power NC2 is my answer. Okay. So we have discussed this theorem many times. So 2 power NC2 is my answer. Take snapshot. I will jump to the next slide.
Okay, sir.
Okay, so how many simple labeled graphs are possible with 5 vertices? So we will say 2 power 5C2 is my answer. That is 2 power 10. That is 1024 answer. Done? How many labeled trees with 4 vertices? Labeled trees. So for that we have formula n power n minus 2. Okay, so 4 power 4 minus 2. I'm not going into the proof. It will simply waste our time. That is 16 is the answer. It is known as Calais formula. Calais is the name of the scientist which has invented this formula. Calais formula. N power n minus 2. Number of labeled trees with 4 vertices. So I think you have studied spanning tree in your algorithms now.
Sir.
Okay, so I think sir have told you this formula for number of spanning trees.
No.
Okay, no problem, no problem. So yeah, take snapshot. I will jump to the next slide.
Copy it, sir.
Okay, so spanning tree and see, spanning tree is subgraph. Tree has individual existence. So that is the basic difference. See this. If I take this A B C D, so spanning tree can be A B like this, A D C B. This is a spanning tree. Okay, so why this is spanning tree? Because it is subgraph of the given graph. Okay, but if this graph is not given and I am just made this, so this is a tree only. It is not a spanning tree. Why? Because spanning tree means subgraph. So you have to give graph and then you can say that I think you have got it. So number of spanning tree or number of trees, one and the same thing only. That is n power n minus 2. This is the Calais formula. Okay. Yeah. Take snapshot. I will jump to the next slide.
Yes, sir.
Okay. So how many labeled rooted trees are possible with n vertices? Rooted means, so now there are n possibilities. Now for example, you have constructed like this A, B, C, D. So now from these A, B, C, D, anyone can be root. So that means n power n minus 2 multiplied by n is the answer, because n possibilities for the root. Okay, so that is nothing but n power n minus 1 is the answer for rooted label trees of n vertices. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so how many labeled subgraphs are possible for Kn? That is very, very important. How many labeled subgraphs are possible for Kn? So subgraph means subgraph can be number of vertices can be zero is not possible. I think you already know zero vertex means nothing. So one vertex, two vertex, three vertex, and so on. You have to take every possibility. So if I take one vertex, so one vertex, how many graphs will be there? So you can take nc1 from n. You take because they are labeled, na. So from n you take you pick any one vertex. So now after picking one vertex, so how many graphs will be possible? Only one. So multiplied by one. Okay. So okay, don't worry, I will tell you. Two. If we take two vertices, you will take nc2. How many graph will be possible with two vertices? So see this one and this one. Okay, so two. For three, nc3. And how many graphs will be possible with three vertices? I think I have told you 2 power 3 c2, no? So 2 power 3 c2, that means 2 power 6. And here I can say 2 power 2 c 2 power 2 c2. 2 power 2 c2. 2 c2 is 1, that's why I have put here 1. Okay, so I think you have got it. So for 4 vertices, nc4 into 2 power 4 c2 dot dot dot, dot like this. Okay, so what we, so finally we will go till ncn into 2 power nc2.
Yes, sir.
Okay, yeah. So that is the number of labeled subgraphs possible for Kn. So if you want to write it in sigma notation, we can simply write it, but we will say n is equal to 1 to, or rather k is equal to 1 to n nck multiplied by 2 power kc2. Please see this. If you have doubt, you can ask me.
Understood.
Is it okay? Okay, yeah. Take snapshot. I will jump to the next slide. Okay, so unlabeled graph counting, I have told you we have to do manually. There is no way out. So manually we are doing. So for example, how many unlabeled graph with 3 vertices? So 0 edge, only 1. Okay, yeah, one edge you may say like this and this, but all are same only, all are isomorphic, na, because there is no labeling, so obviously 1. So 2 edges, all these are same, only 1. 3 edges, only 1. So I think we will count like this only. 3 vertices are there. So what are the possibilities? 0 edge, 1 edge, 2 edge, 3 edge, all are 1. So 4 is the answer. Okay, yeah, take snapshot. I will jump to the next slide. Okay, so how many labeled non-isomorphic graphs with 3 vertices? Labeled non-isomorphic means you can consider it as just like unlabeled. Okay, because I can say like this. So A, B, C, and if you make B, A, C, no problem. They are isomorphic only. Just labeling is different, na. So directly I want to say labeling does not matter. When labeling does not matter, it is nothing but you are unlabeled only. So no need to worry. So they will just confuse you. Labeled non-isomorphic. Labeled non-isomorphic mean unlabeled only. With 3 vertices, answer is 4. That's it. We have told you in the previous slide only. 4 is the answer. Okay. Yeah. So take snapshot. I will jump to the next slide. Done?
Done, sir.
Okay, so 4 vertices, unlabeled graph. So 4 vertices, so see this 0 edge, same scenario, 0 edge, 1. So 4 vertices, by the way, how many edges we can take? 4 vertices, 4 C2, that means 6 edges we can take. So from 0 to 6, I will do it. For 1 edge, only 1. Okay, so all these are same only. For 2 edges, only 2. Why? Because you might say, sir, okay, these are different, but this and this are same only. So no need to worry. And this and this are same only. No need to worry. Okay, so only 2 we have got. 3 edges, so this and this. Okay, yeah, so actually this is not correct, because if you twist it, you will get this only. So we should say like this. So A, B, C, so 4 vertices, triangle, and 1 vertex extra. So 3 are there. Okay, yes, and 4 edges, only 2, 5 only 1, 6 only 1. You can check it out yourself. So what will be our answer? 11 is the answer. And I have told you how to remember it. 0, 6, same. 1 and 5, same. 2 and 4, same. You can check this out. 0 and 6, only 1 and only 1, like this. So 11 is the answer. Take snapshot. I will jump to the next slide. Done? Oh, okay, so final summary: 1 vertex, 2 vertex, 3 vertex, 4 vertex, labeled 1, 2, 8, 64, and unlabeled are 1, 2, 4, and 11. We have just studied it. Take snapshot. I will jump to the next slide.
Done, sir.
So graph numbers we are going to start. It is again very important topic. Many times question have been asked. Chromatic number, independence number, domination number, matching number, and covering number. Total 5 graph number we have to study. Take snapshot. I will start with chromatic number. Done.
Sir. Sir.
Okay, so what is chromatic number? Chromatic number is represented by kg. We have studied in the previous class also, but we will study few theorems here that are very important. So minimum number of colors needed to properly color the graph. Properly means no two vertices should be, no two adjacent vertices have same color. I have told you in the previous lectures only. So I am not writing it just to save the time. Okay, so this is black, or you can say red or red, or non-adjacent we will take. Okay, and then here green. Okay, now here we have to take blue, and here we can take say green only. Okay, so three kg is 3. Take snapshot. I will jump to the next slide. Done. Okay, so kg is always unique for a graph. That is, no two persons can get different answers. No doubt color used may be different, but number of colors is same. I think you already know, na? Chromatic number means minimum number of colors, so number is same, na? So you might take cyan, magenta, yellow, whatever colors you want, you can take, but number is same. Okay, 3. You will get 3 as the answer. So that is what I have written here. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so this is the graph given to us. What is the kg? We have to find it out. So see this. Before studying that, I have given you a theorem that if largest click in a graph G is of size n, then kg will be greater than or equal to n. Kn click is what? Complete graph as subgraph of the given graph. Complete graph as subgraph of given graph. So here, what is the largest click here? So largest click here is 3. That means k3 is there. So what I will say, if largest click in subgraph in graph G is of size n, then kg will be greater than or equal to n. That is for sure. So k3 is there. So I will say kg will be greater than or equal to 3 here. So we can check that out. For example, here I have given red. So here also I can give red. Okay, here also I can give red. Now, okay, that's it. So here I will take blue. So here I will take blue, and then here I will take green. Okay, and what I have to take here? Yellow. So 4 I am taking. So is there any other way to get any other answer? Let me check that out. So here, let us suppose, okay, so we can start with vertex say here. If I take here green, so these 4 vertices cannot be green. So I take here say blue. Now here I can take blue, here I can take blue, no problem. So now this is left. So I have to take here say yellow. Okay, so here I have taken yellow. Okay, so now here what I can take here also yellow, and here I can take green. Yeah, so 3 are sufficient. So the moment I get 3, I will say I cannot get less than 3. No need to retry it. For if previously I have got 4, that's why I retried, because it should be greater than or equal to 3. No doubt 4 is greater than or equal to 3, but minimum is 3. We cannot get less than 3. So I tried to get 3 as answer, and I have got it. I got success. So I will stop here itself. I will not say that you have to try to lower it down further. I cannot lower it down. Okay, so 3 is the answer. Now what about here? So here we have K4, na? K4 is there. So I will say Kg will be greater than or equal to 4 here. Okay, so what I will say, so our approach will be, you try to attack that vertex which is adjacent to many vertices. Okay, so for example, I can take this vertex. This is adjacent to many vertices. So better you give it some color, say green. I have given it. So the moment I have given green, so other I cannot give green. So let us suppose I take here blue. Okay, so here also blue, here also blue. Okay, and any other, here also blue. Okay, so any other? Yeah, that's it. So next is yellow. So let us suppose I take here yellow. Okay, and here here I can take yellow, and then say I take magenta here. Yeah, and here also I can take magenta. Okay, so 4 colors, no? 4 colors are sufficient. Yes, please come again if you have doubt.
Yeah, no, sir, I understood, because the green comes and touch there where the magenta has been taken. The vertex comes from green.
Okay, so here we have taken green. So
Yeah,
here
no.
also we can take green, na? Okay, you want to say like this? We can take here green.
No, sir. I actually, after blue magenta you took, though I was actually feeling bad. But there is a
Okay, okay, okay,
edge
okay.
comes from.
Okay, so you can no,
No,
but we
sir.
cannot take green now because they are adjacent.
Yes, yes, sir. Yes, sir.
Okay, so finally we have got four. Four as the answer. Minimum is four. So we will not retry it and try to check whether we can take three colors or
Yes.
not. That is the power of this theorem. Okay, so here answer we are
Okay.
getting is four. No need to worry. Take snapshot. I will jump to the next slide. Done.
Done, sir.
Okay. So next theorem is kg will be minimum one and a maximum n. One for null graph and n for complete graph of n vertices. In the previous lectures also I have told you. Take snapshot.
Yes,
Okay.
sir. Done.
So kg for standard graph I have told you in the previous lectures only. Phi n was 1, kn is for n, cn when n is even it is 2, 3 when n is odd. For wn we have told you all these things. So take just snapshot. I will
Yes.
jump to the next slide. Okay.
Done, sir.
Yeah. So next is kg for tree. Tree is bipartite, na? Since every tree is bipartite, so only two colors are sufficient. So for tree, I have not told you that tree contain two or more vertices. So we can take one vertex also. So one kg less than or equal to two. This is the range. So one or two. One if trivial tree we are taking, and two if non-trivial tree.
Yes, sir.
Yeah, take snapshot. I will jump to the next slide.
Done, sir.
Okay, kg for planar graph. So this is four color theorem. I am not going into the proof of it. So kg for planar graph will be so 1 2 less than kg less than equal to 4. Okay. So 1 to 4 is the range. You will not need five colors. If for a planar graph by chance you have taken five colors, you have to review it and you have to check it out again. Four colors are more than sufficient. Okay.
Yes,
So
sir.
kg for planar graph maximum four you need, minimum one because phi n is also planar. Okay, maximum four. Okay, so for example k5 you take. So obviously for complete graph of n vertices, chromatic number was n, na? So here this vertex is adjacent to all the vertices. So obviously here kg will be equal to 5 and it is non-planar. That's why we are getting 5. So if for planar graph you are getting 5, you have to check that out again. You might need 4 also. Okay, rather 4 should be your answer. Okay, yeah,
Yes.
take snapshot. I will jump to the next slide.
Done,
Okay, so kg for planar graph having cycle of length 3, directly indirectly they want to say cycle of length 3 means k3 is present. K3 is present as subgraph, so chromatic number will be greater than or equal to 3, that is for sure. And they are saying planar also, so kg will be between 3 to 4, that is the range. Take snapshot. I will jump to the next slide.
done, sir.
Okay, range of kg for planar graph which is not null graph. So that is very simple. Okay. So
Yes,
if
sir.
it is not null graph, then minimum two, na? Yeah. Take snapshot. I will jump to the next slide.
Copied, sir.
Okay. So theorem kg is less than equal to 1 plus delta. Delta is the maximum degree, na? So 1 plus delta kg will be less than or equal to that. So maximum degree. So for example, I have a vertex here and it is connected to say four other vertices. So what I will say, if I take here blue, then obviously I can take here green, 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 green. So two are sufficient. No need to worry. So 2 is less than or equal to 1 plus delta. Delta here is 4. Our theorem is satisfied.
Yes.
So you can connect them any way you want. It need not worry me. The only thing is if you have a maximum degree vertex, then 1 plus maximum degree vertex kg should be less than or equal to that only. Okay, so extreme case will be your complete graph. So for example here I have taken k4. So what is the maximum degree? Delta. So it is a regular graph, na? So delta is 3, maximum degree or minimum degree, everything is 3 here. So regular graph. So what is kg here? Kg is less than equal to 1 plus delta. That means kg should be less than equal to 4, and here obviously you are getting 4 as the answer. So this is the upper limit. Okay, so kg is less than equal to 1 plus delta. You should know this theorem.
Yes. But
Take
I
snap
did not
and
understand here below, sir.
please come again.
This figure where you, uh, the
This
the bottom figure, sir. Bottom,
Okay,
bottom.
but I was just showing you that if I give here blue color, then everywhere you can give green. But if I join them,
But
if I join them,
huh,
then we have to take different colors. So for example, here green, here say yellow, and here I do not know how I have built it. I have just given you the idea. So the basic idea was 4 plus 1 5. So chromatic number will be less than or equal to 5. That is the basic thing.
okay, sir.
Yeah. Take snapshot. I will jump to the next slide.
Done, sir.
Okay. So in a graph with delta is 6, kg can be at most 1 plus delta. That means 7. B. Take snapshot.
Done, sir.
So kg for multigraph can be found by reducing it to simple graph, because see if we have multigraph like this, obviously you can convert it into simple graph like this, and you will simply say that if we have given here red, you have to give here green. That means you cannot take red here. So for chromatic number, we just need that they are connected or not, they have an edge or not. If they have an edge, then you cannot take the same color. So it hardly matters you take 1 edge, 2 edge, 3 edge or infinite edges. It hardly matters. So simply I will convert multigraph to simple graph, and then I can solve and get the answer for chromatic number. Any doubt?
No, sir.
Yeah, take snapshot. Done?
Done, sir.
Okay. So for example, here I want to find kg. So it is a multigraph. No need to worry. You just make it like this. So red, red, green, green. So 2 is the answer. That's it. Okay.
Yes, sir.
Yeah. So let me jump to the next slide. So this is again okay. So you might say that this is a you can say there is a parallel edge or something like that, but no, there is no parallel edge. You try to think about it. So this is A and C. There is no other edge between A and C. So this is triangle with this like this. Are you able to visualize?
Yes, sir.
Yeah. So
Yes,
what is the chromatic number here? So okay, I have already written it. So if I take here red, okay, so what color I can take here? Blue, and here green, and here I can take red. So 3 is sufficient for us. Okay, and by the way, since it has a K3 as a subgraph in it, so that means largest click is K3 here. So obviously greater than or equal to 3 should be our answer, and we have got 3. So we will stop here itself, and we will not check further.
Yes, sir.
Take snapshot. I will jump to the next slide. Done? Okay.
Yes,
So pseudograph kg. So see this pseudograph can have self loop. So this A vertex is adjacent to itself. So which color I should give here? If I give here red, I will say this. So 2 adjacent vertices are having same color. I cannot say like this. Okay. So pseudograph kg concept is not there. Okay. So chromatic number concept is not for pseudograph. It is for multigraph or simple graph. Multi or simple. And anyway, multi is converted to simple only because we just want to say whether edge present or not. Take snapshot. I will jump to the next slide. Okay. Yeah. So a graph G is K colorable if and only if it can be properly colored by minimum K colors. So it's just a terminology. K colorable means minimum K colors are needed. That means hence 3 colorable graph means Kg is 3. So if chromatic number 3, I will say it is 3 colorable. It is just a simple term. Okay. Take snapshot. Okay. So 3 colorable graph cannot be properly colored by, obviously it cannot properly colored by 2 colors. 3 colorable means Kg is 3. Kg3 means minimum color needed is 3. So how you can color it by 2 colors? Not possible. Properly colored, na? So 2 is the answer. Any doubt?
No, sir.
Okay. So let me jump to the next slide. So independent set, stable set, co-click or anti-click. That is a different definition. Now we are jumping to that. So chromatic number is over now. Okay. So now we are going to start independence number. So next graph number is independence number. See the slide. I have told you. So what was that? Graph numbers. Now chromatic number is over. Now we are going to start independence number. Okay. So let me start the independence number now. So chromatic number, I have shown you many theorems and all. These are very, very important. Okay. So before starting independence number, I am building some background. Okay. then I will jump to the independence number. So first I'm going to explain what is independent set, stable set, co-click or anti-click. One and the same thing. The terminology have been used in different books. So set of pairwise non-adjacent vertices. Set of pairwise non-adjacent vertices, independent set. For example, this graph is given to us A, B, and E. So A, B are adjacent. Forget about it. It is not independent set. A, D, C, F. A, D, C, and F. Yeah. So you can
Yes.
pick any pair. There is no edge between them. A, E. Yes. Independent set. A, E, G. A, E, G. No, it is not.
No,
A,
sir.
yes. E, yes. 100% single vertex. So no problem. No edge. Okay. Yeah. So single vertex is always an independent set. That is I have written here. Take snapshot. I will
Okay,
jump to
sir.
the next slide.
Done,
Okay.
sir.
Yeah, so next is maximal independent set. Independent set we have done. Now it is maximal. Maximal means even if you add, maximal means it is already maximal. So maximal means you cannot add. Maximal means you cannot add. Minimal means you cannot subtract. Minimal means you cannot subtract. So maximal means even if you add one more vertex to the set, independence property is disturbed. That is, it is no longer remain independent set. So set AD. AD is independent set. Yes, it is independent. Is it maximal? No, because you can add G to it also. ADG is also independent, so it is not maximal. AE. AE, yes, it is independent. Of course, they are non-adjacent. And can I add any other vertex? See, B I cannot add because it
No.
is adjacent to A. So no other vertex. Yes, so it is not maximal. Sorry, it is maximal. It is maximal because I cannot add any extra vertex. BE, same is the case with BE. Yes, it is independent set and it is maximal also. ADC, A, D, and C. So they are yeah. So I can add G to it. So it is not maximal, but it is independent. ADCF, A, D, C, and F. Yeah. So I cannot add anything extra maximal, and it is also independent set. ADCF, you can check it out. ADCG, ADCG. Yeah, it is also maximal. Take snapshot. I will jump to the next slide.
Done, sir.
Okay. So next is conclusion. Finally, independent set is unique. No, I have told you many independent sets are there. Maximal independent set unique. No, I have told you many maximal independent sets were there. Largest maximal independent set is unique. No, see this large maximal independent set 2. Largest maximal independent set but 2 here. Okay, so it is not unique. But size of largest maximal independent set, yes, it is unique for sure, and that is nothing but your independence number. Okay, so independent number is size of the largest maximal independent set, and that is 4 here. So for this graph, independence number is 4. Independence number is
Yes.
4 for this graph. Okay, yeah. So you can take snapshot of this. I will jump to the next slide.
Done, sir.
Okay, so independence number beta G. Beta G is size of the largest maximal independent set. Take snapshot. And
Okay.
you should know independence number is represented by beta G. Beta G is the symbol for it. Anyway, it is not standard symbol. I am following Narsingh Dev book. So in this book they have used this symbol. In GATE exam, if they want to use any other symbol, they will properly mention that this is the symbol we are using for independence number. Yeah. So let me jump to the next slide. So algorithm to find beta G. Algorithm is very simple. So we want to find maximal or minimal. We want to find maximal. Minimal is trivial. Why we are not finding minimal? Minimal is trivial. You can take A. This is a minimal independent set. No need to worry. So it is trivial. We want maximal independent set. So how to find maximal? So should you target a vertex which is adjacent to many other, or you should target a vertex which is adjacent to very less? We will target a vertex which is adjacent to very less vertices, because if I take E, then obviously I cannot take F, G, C, D. That will create a problem for us. So we will not attack that vertex which is adjacent to many vertices. We should attack that vertex which is adjacent to very less vertices. So I will start from A. After taking A, what should I take? B is adjacent to 3 vertices. That I have taken A now. So B I cannot take. Never. I cannot take B. So the moment I have taken A, I will cross B. Screen is visible or not?
It is visible, sir.
Movement is there?
Yes, sir. Yes, sir.
Okay. So yes. So A I have taken, B I will cross. Why? Because B will be adjacent. I have to take non-adjacent. D. Yes, D I can take. The moment I take D, I will cross E. Okay, and why I have taken D? Because it was having very less degree, or it was adjacent to very few vertices. If I take E, that will create problem again. So I have not taken it. So now can I take C here? Yes, I can take C. No need to worry. So the moment I have taken C, I will cut it, and adjacent already are cut, no problem. Now F and G are left. You can take any one, F or G. If I take F, no problem. Even if I take G, also no problem.
Yes.
Okay. So that is the algorithm to find beta G. So you attack. So in one word, if I want to write, I will say attack vertex with minimum degree. Vertices of minimum degree. Okay. So they are adjacent to very less vertices. You should attack them because we want to find maximal, na? No, maximal. That's why. Take snapshot. I will jump to the next slide.
Done, sir.
Okay. So theorem, beta G will be greater than or equal to n upon kg. Kg was your chromatic number. This is the relationship between beta G and kg. You have to remember this. If you want proof, then I can give you. It is on my next slide. Take snapshot first.
Done, sir.
Okay. So I will not dig deep into it. I'm just giving you idea. So if n is 9 and kg is 3, then 3 different colors are used. Okay, so 9 vertices graph is there and chromatic number is 3. That means 3 different colors are used. So we can have 3 different set of vertices, and vertices in each set are non-adjacent. I think you have got it. So 9, so R, G and B. Okay, so here 3 vertices you can take, here 3 and here 3. That is the maximum which you can take. Okay, yeah. So according to Pigeonhole principle, there exists at least one set whose size is greater than or equal to n by 3. That is n upon kg ceiling function. So beta G will be greater than or equal to n by kg ceiling function. So this is a proof. If you are able to get it, it's okay. If you are not able to get it, don't worry. In the recording, you can watch it. We should not waste time in the proof and all because time is very less. You should know this formula very properly. Beta G should be greater than or equal to n upon kg ceiling function.
Done, sir.
Okay, so next beta G for Kn. So beta G for Kn will be what? So complete graph of n vertices. So what should be our answer? So obviously, if we take this, so only one, na? Only one. So beta G will be equal to 1. Okay. So maximal independent set will contain only one vertex, because the moment you try to put any other vertex, for example, A I have taken. So now which vertex you can take? All are adjacent to it. So only one. So beta G will be 1. Okay, and you can put the formula also. Beta G should be greater than or equal to n upon kg ceiling function. So n is what here? Kg for Kn will be n itself. So beta G will be greater than or equal to 1. And here 1 we have got it. Any doubt?
Done, sir. No.
Take snapshot. I will jump to the next slide.
Done, sir.
Next is domination number. So domination number, so same scenario. Okay, just like independence number, I have built what is independent set and so on. Same way I will build the background, and then we will start the next number, that is domination number. So first of all, we will need to know what is domination set. So it is set of vertices such that every vertex in G is either in dominating set or within one edge from any other vertex in the dominating set. So simply I want to say that this is set of vertices which dominate the entire graph. Dominate the entire graph means you name any vertex, I will be able to reach that vertex within one edge or within 0 edge. For example, this is a graph, this is a big graph, okay, and I am saying that this is the set of vertices which is dominating set. That means you just name any vertex, I will be able to reach that vertex with one of the vertex from here. That means there should be an edge from one of the vertex to that vertex, or that vertex should be in this set only. If it is in this set only, no problem. If it is outside, then you have to take only one edge. So you can think like that. Politicians, how they win the election? So they will pick those persons who know many persons. So they will approach one person like this. So do you know Narendra Modi privately? No, we do not know him personally. So how he got your vote? Because he knows some other person, and that person know your politician in your area, and that politician approach you and he said you to give vote, you give him vote, indirectly vote was given to Narendra Modi. That is the scenario we are taking here. So this is exactly what politicians are doing. So they will approach so they will make a group of person who know almost every person in your area. Okay, so if they approach all these persons, so if he wants to know the phone number of any other person, so he will contact the persons in his set, and somebody definitely know the phone number of you, so he or she can contact you very easily. Okay, that is the basic meaning of dominating set. So this set is dominating your entire city. So this set of persons are dominating your entire city, because now these are the person who know each and everyone in your city, just like that. That is the dominating set.
Yes.
Okay, so see this I have written here. Simply we can say that dominating set is such a set of vertices which dominate the entire graph, in the sense that entire graph is reachable from that set in at most one step. That is, if vertex in set already, then we assume 0 step or edge. But if vertex is not in the set, then by one edge we must reach the given vertex from any vertex in the set. Okay, take snapshot. I will jump to the next slide. Done. Okay, so I think you have got the dominating set. So E is dominating set? No, because from E you can reach F, G, C, D. What about B and A? You will not reach from E to B and A. So it is not dominating set. A and E, yes, it is dominating set. Why? Because from A you can reach B. From E you can reach all other. Yes, it is dominating. B and E, yes, 100%. So from E you can reach these 4. From B you can reach the A. So if you know these 2 persons, so directly you know everyone in the city. That is the beauty of politics.
Yes.
So you just know one person who knows many persons. So indirectly everybody knows you, like this. So ADCF, A, D, C and F. Yes, everything will be covered, because A will cover B. Okay, D will cover E. Yeah. So similarly A, B, C, D, E, F, G. If you take all, that is trivial. 100% it is dominating set. That is trivial, na? If you take everyone, it is very trivial. It will be dominating set. So clearly now you have got it. We are interested in maximal dominating set or minimal dominating set. We are interested in minimal. We are not interested in maximal, because this is big. We are not interested in that. So who is good politician? So if he spend very less amount of money and still he is able to grab the votes, that means he should grab only those person who knows many other person. So he is the most demanding person, because he knows many other person in your city. So politician will definitely approach this E. Okay,
Yes.
so we are interested in minimal dominating set. We are not interested in maximal. Maximal means you take everyone. Okay, yeah. So but in independence, we were interested in maximal independent set. We were not interested in minimal independent set. Minimal means you take only one vertex. Okay, take snapshot. I will jump to the next slide. So minimal dominating set. So minimal means.
Next slide.
Yeah, please come again.
Yeah. I took it now, sir.
Okay, yes. So minimal dominating set definition. Minimal means even if we remove one vertex from the set, dominating set property is disturbed. That is no longer remain dominating set. Okay. So here we are not interested in maximal because it is trivial. That is a set of all vertices in G. We are interested in minimal dominating set only. I have told you these points. Take snapshot.
Yes, sir.
Done. Okay, so see this. So dominating set, and this is minimal dominating set. E, no. So no possibility of minimal dominating set, because it is not even dominating set. AE, yes, it is dominating set. It is minimal, yes, 100% it is minimal. Why? Because you cannot subtract E or A or E from this set. Okay, BE, yes, 100% it is minimal. ADCF, so ADCF, is it minimal or not? It is dominating, yes, 100% is dominating. So can I subtract A from here? If I subtract A, then DCF can cover C. D cannot cover A. Okay, so D cannot cover A. Why? And C cannot cover A, F cannot cover A, so I cannot delete A. Similarly, I cannot delete D, C, F, so it is minimal also. A, B, C, D, E, F, G, yes, it is dominating, but it is not minimal for sure, because I can delete A. The moment I delete A, B can reach A, no problem. Okay, so it is not minimal. Yeah, so take snapshot. I will jump to the next slide. Done. Okay, so now same thing which I have showed you in independent set. Dominating set unique? No. There are many dominating set. Minimal dominating set unique? No. There are many minimal. See this and this also.
Yes.
3. Smallest minimal dominating set unique? No. See this. There are 2. Okay, it is not unique. But size, yes, this is unique, and that is your dominating number. Domination number, that is alpha G. Domination number is represented by alpha G. Okay, take snapshot. I will jump to the next slide. Okay, so domination number alpha G, size of the smallest minimal dominating set, that is domination number. Take snapshot. Done. Okay, So algorithm to find alpha G. So how you will find alpha G? I have told you politician who politician will approach that person who know many other persons. So obviously first we will approach E. The moment we approach E, F, G, D, C are covered. Now it's your choice. You either take A or B. So you take A or you take B. So that is the algorithm to find alpha G. So what number is 2? Okay, only 2. Take snapshot. I will
Okay.
jump to the next.
Done, sir.
Okay, so theorem MIS means MDS. So it is one way theorem. MIS, minimal independent set. If it is minimal independent set, it will be sorry, maximal. Sorry for that. Maximal independent set. If it is maximal independent set, then it will be minimal dominating set. That is for sure. Proof I have given you the next slide. Take snapshot.
Done, sir.
Done. Okay, so but this is the proof. Independent set is maximal. That is, we can't put any other vertex in this set because its independence property will be destroyed. That means if you put any other vertex, that will be adjacent one. So we have taken all the non-adjacent vertices. Now indirectly it means other vertices are exactly one edge from any other vertices in MIS, which is nothing but your dominating set only. Are you getting it? No.
Yes, sir.
Okay, so
No, I already.
okay, yes. So next is it will be minimal dominating set. That is, we can't remove any vertex from it, because if we remove any vertex and still it remain dominating set, then that vertex must be adjacent to any other vertex in the set, but it is impossible because we already said it is independent set. Okay, so you can read it out. If you have any doubt, you can ask me in the next lecture. It is very simple
Yes.
what I have written. So take snapshot. I will jump to the next slide.
Done, sir.
Okay, so theorem, another theorem, alpha G is less than equal to beta G. Take snapshot.
Answer.
Okay, so proof I have given you. Beta G is the size of the largest maximal independent set. Since it is maximal independent set, so it will be a minimal dominating set also. Okay, now since alpha G is size of the smallest minimal dominating set and beta G is indirectly size of the minimal dominating set, hence alpha G will be less than equal to beta G. Okay, so I think it is very simple. But see this, if you want me, then I can explain. Beta G is size of the largest maximal independent set, and since it is maximum independent set, from the previous theorem which I have told you, it will be minimal dominating set. Okay, so now alpha G is the size of the smallest minimal dominating set. Alpha G is size of smallest minimal dominating set, but beta G is any other minimal dominating set. So it may or may not be smallest. So since alpha G is smallest and beta G may or may not be smallest, so alpha G is less than equal to beta G. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so next is matching number. Yeah, so what is matching number? Okay, so I think time is left. I think 10. So yeah, we have 40 minutes left. So I will now slow down, and now I will try to give you proof and all slowly. No need to worry. We have sufficient time. Okay, so what is matching number? Matching means set of edges which are non-adjacent. Okay, what do you mean by matching? Matching means set of edges which are non-adjacent. Now set of vertices which are non-adjacent is independent set. Non-adjacent means a common vertex should not be there. Okay, common vertex not allowed. So matching is set of edges which are non-adjacent, but set of vertices which are non-adjacent is independent set. Okay, so hence concept of matching is similar to independent set. So only difference is independent set is for vertices and matching is for edges. Let me give you idea, you will get more clarity from this example. E2, clearly it is matching. Okay, because it is non-adjacent, so we have not taken any other edge, so clearly it is proper, no problem. E2, E5, E2 and E5, they are adjacent edges because one vertex is common, so it is not matching. E2, E7, E2 and E7, yes, it is matching. E1, E2, E3, E8, E1, E2, no immediately cut because E1, E2 common vertex is there. E3, E5, E8, E3, E5, E8, yes, clearly it is okay. Okay, so so independent set was for vertices, but matching is for edges. That is the basic difference. Okay, yeah, so single edge is always matching. I have told you it is always matching because no other edge is there, which is creating problem for him. Okay, take snapshot. I will come to the next slide.
Done, sir.
Okay, So now obviously we are interested in maximal matching or minimal matching. Minimal matching is trivial. You take any edge that is minimal. So we are interested in maximal. So just like we were interested in maximal independent set. We were not interested in minimal independent set. Same is the case here. We are interested in maximal matching. So see this. I have written here. Maximal means even if you add one more edge, the set to the set, matching property will be disturbed. That is, it is no longer remain matching. So we are interested in maximal matching. Maximal matching. But minimal matching we are not interested because minimal matching is trivial. Minimal matching is trivial. Okay, we are not interested in it. Single edge. So just like maximal matching is just like your maximal independent set. Okay. Yes. So see here, set E2. Clearly it is matching. It is not maximal because we can add many edges. E2 E5, E2 E5. It is not a matching. So forget about maximal. E2 E7. Yes, it is matching. But is it maximal? E2 E7. Can you add any other edge? Yes, we can add E6 to it. So it is not maximal. E1, E2, E3, E8. E1, okay. E2. Forget about it because E1 and E2 are adjacent. E3, E5, E8. E3, E5, E8. If you take them, yes, it is matching for sure. Is it maximal? Is it maximal? So for maximal, can you add E1? No. Can you add E2? No. E4? No. E7? No. E6? No. So yes, it is maximal. E1, E5? Yes, it is matching. Is it maximal? E1 and E5 if you take. Let me rub that. If you take E1 and E5, E1 and E5. So now can you add another? Yes, we can add E8 to it. So no problem. It is not. It is not maximal. Okay, it is matching, but it is not maximal. E1, E5, E8. E1, E5, E8. Yes, it is matching. Is it maximal? Yes, it is maximal also. We cannot add any extra. Yes. So now same scenario, just like that in the previous we have seen numbers. Same scenario. Let me jump to the next slide. You will get more clarity. Yes.
I
So
copy
same.
that, sir.
Hmm.
I need to take a.
Okay. 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 Take it.
Done, sir.
Okay. So same. Matching is unique. No, we have seen many matching are there. So minimal matching unique. No, we have said here. Sorry, maximal matching. No, MM means maximal matching. Maximal matching unique. No. See, this was see this. This was maximal. This was also okay. Where was that? This was maximal and this was maximal. It is not unique. Largest matching unique? No. There are many largest matching. These two are. So size of largest matching unique? Yes, that is for sure. And that is your matching number. So same. I think you have got it. Na? Same way I have written everything. So that everything become
Yes, sir.
trivial, and I have linked the topic so that you get more clarity and very easily you will get all the things. Okay. So this is your matching number. Take snapshot. I will jump to the next slide.
Done, sir.
So same. Matching number is size of the largest matching. Done.
Yes, sir.
Okay, so what is the algorithm to find matching number? So which edges you should attack first? That is common sense, just like your maximal independent set. So we were trying to attack those vertices which were adjacent to very less vertices. So same is the scenario here. You can attack E1 first because with E1 only two edges are there. Okay, and with E2 two edges are there. So you can attack anyone. So I have attacked E1 first. Okay, after taking E1, E2 and E3 are gone. You can take E5. After taking E5, E4, E7, E6 are gone, and then you can take E8. Like this you can make. Okay, so try to attack that edge which is adjacent to very less number of edges. Okay, so anyway I have taken here E5 first. Actually I should not take E5 because E5 is adjacent to many other edges. So first of all we should take E8 first. Okay, so anyway answer is same, but no problem. E1 we have taken, then we will take E8. After taking E8, so we will cut E7 and E6. Now you have a choice. You can take either E5 or E4. If I take E5, we will get this. If I take E4, we will get another.
Yes, sir.
Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so next is covering number. Covering number means cover is what? Set of edges which cover all vertices of graph. What is cover? Cover is set of edges which cover all the vertices of graph. Okay, so it is just like dominating set. Dominating set was a set of vertices which cover all the vertices, but here set of edges which cover all the vertices of graph. It is the edges, set of edges. It was set of vertices which cover all the uh, entire graph. That was dominating set. So it is set of edges. So for example, see this. So I have to cover all the vertices of graph. For example, if I take E1, obviously E1 is not the answer because it will cover only two vertices A and B. But about other vertices, it is not. E1, E2, yeah, no, because we are left with C, E, F, G. We have not covered them. E1, E5, E4, E8, E1, E5, E4, E8. Everything is covered now. AB is covered. DE is covered. C, A, E, F. Yes, it is okay. E1, E2, E4, E8. E1. Okay, let me take it bigger now. Now it is good. E1, E2, E4, E8. E1, E2, E4, E8. Yes. E1 is covering A and B. E2 is covering D, C and E, F and G. Yes, everything is covered. No problem. E1, E5, E4, E7, E6. E1, E5, E4, E7, E6. Yes, no problem. Similarly here, this is trivial. Na? You have covered all. You have taken all the edges. Obviously, every vertex will be covered. No need to worry. Okay, everything will be covered here. So obviously, just like dominating set, uh, we are interested in minimal cover. We are not interested in maximal because maximal is trivial. You take all. That is very simple. Okay, so we are interested in minimal cover. Let me jump
Yeah.
to the next slide. Take snapshot.
Thanks, sir.
Okay, so yeah, here we have written also. We are interested in minimal cover. Minimal means even if you remove one edge from the set, covering property is disturbed. That is, it is no longer remain the cover. Okay, so for example, E1 it is not a cover. Forget about minimal. E1 it is not a cover. Forget about minimal. E1, E5, E4, E8. Yes, it was cover. Is it minimal? So see this E1, E5, E4, E8. Yes, everything is covered. Now, even if you delete one of the edge, so vertex might not be covered. For example, E5 is deleted, D will not be covered. E4 is deleted, C will not be covered, and so on. Yes, it is minimal. E1, E2, E4, E8. E1, E2, E4, E8. So E1 is deleted, then A will not be covered. Now E2 deleted, then D will not be covered. Okay, E4 deleted, then E will not be covered. So here E8 deleted, then F and G will not be covered. Yes, so obviously it is minimal. Okay, so it is also minimal. And what about this? 1, 2, 3, 4, 5. And one more thing, I think by common sense you can guess this out. So there were 4 edges here. So each edge will join 2 vertices. So obviously here how many vertices are there? 1, 2, 3, 4, 5, 6 and 7 vertices are there. So we need at least 4 edges. With 3 edges you can cover only 6 vertices. 7th vertex will be left out. So if we have 4 edges and we say it is a cover, 100% it will be a minimal cover. Are you getting it?
Huh.
Okay, so at least 4 are needed. So here we have got 5. So now there is a doubt in my mind that it might not be minimal. So that is covered. Let me check that out. E1, E5, E4,
So
E7 and
E7.
E8. So E7 we can delete easily because if I delete E7, everything is covered. No problem. Okay,
Yes,
so
yes.
it is covered, but it is not minimal. Okay. Similarly here, I think it is very trivial. It is covered, but it is not minimal because many edges are extra here. Take snapshot.
Done,
I
sir.
will jump to the next slide. Done. Okay. So final conclusion same. I think you have got it. Cover unique? No. Minimal cover unique? No. Serious? Minimal cover. This was also minimal. This was also minimum. Two were minimal. Smallest cover unique? No. Smallest cover, there are two smallest cover. They are not unique. Size, yes, it is unique, and that is known as covering number.
Done.
Take snapshot. I will jump to the next slide. Okay.
Done.
Yeah. So what is the theorem? Covering number is greater than or equal to n by 2. I have just told you, na. So whatever cover you take, its size should be at least n by 2 ceiling function. For example, 7 vertices were there, 7 by 2 ceiling function. That means 4. 4 edges at least you have to take. If you take 3 edges, you can cover 6 vertices only. Where what about 7? So that's why I have taken here ceiling function. So 3.5 vertex is meaningless. Okay, 7 by 2 is 3.5. 3.5 is meaningless. Either you have to take 3 or you have to take 4. If you take 3, you will be able to cover 6 vertices. You cannot cover the 7th one. That's why we have said ceiling function. 4 is the answer. Okay, so this is very simple theorem. Take snapshot. I will jump to the next slide.
Done.
Okay. Graph of order 10 has covering number at least. So graph of order 10. So 10 by 2 ceiling function, that is 5. At least 5. Okay.
Yes, sir.
See this. Yeah, we have theorem here, na? N by 2 ceiling function. So at least we are saying that means greater than or equal to 5. Take snapshot.
Done, sir.
Okay. So how to find the smallest minimal cover? So for that we have algorithm. Algorithm is very simple. You include all the pendant edges, because if pendant edge is not included, then pendant vertex will never be covered. Okay. For example, here see this. If I do not cover even, if I do not take even, there is no way out to reach vertex A. So you have to include even. That is the pendant edge. Now pendant edge means which cover pendant vertex. Pendant vertex means degree 1 vertex. In the starting graph theory, I have told you, na. So just imagine it just like pendulum in your watch. Okay, so in wall clock we have pendulum, na. So from here we have got the pendant word. So this is pendulum. Okay, so degree 1 vertex you can consider it. That's why we take it as pendant vertex. Okay, so degree 1. Yes, so step 1 was include all the pendant edges, because if pendant edge is not included, then pendant vertex will never be covered. Hence every cover, minimal or not, must include every pendant edge. Okay, whether it is minimal cover or it is not minimal cover, it hardly matters. We have to include every pendant edge. Okay, next, include edges in such a way that 2 new vertices are covered by every edge, and in last include edges which can cover 1 new vertex and stop when all vertices are covered. So this means, like for example, okay, so I will explain this algorithm here. So I have to include even, because without even I cannot cover everything. Next, now I will try to cover those edges with which I can add 2 new vertices. Okay, if I take E2, E2 will not help us. Why? Because B is already covered. So if I take E2, only D will be covered now. Are you getting it? See this. Let me write it. Because I have taken E1, I have taken A and B. 2 vertices are covered. Because of E1,
Yes, sir.
2 vertices are covered. Now, and it was pendant. We have to take it. So for step number 1, I have taken E1. Okay, why I have taken E1? Because of step number 1. Because every pendant edge should be taken. That is for sure. Next, I should not take E2 or E3 because they will add only 1. Can I take E5? Yes. E4? Yes. E7? Yes. E6? Yes. E8? Yes. So it's your choice. Whatever way you want, you can take. I will take, say, for example, E5 first. If I take E5, then I have covered D and D. So are you getting it now? So I will take that edge which will cover 2 or more vertices. Yeah. Next. So if I take E2, no, it will cover B and D. By the way, they are already covered, so never include E2. E2 inclusion is not allowed because already vertices are covered. E3, E3 inclusion is allowed, but it will add only 1 new vertex. I will not take it. EF, no. So that means E7. E7, no. E6, no. E8, yes. Because if I take E8, I will cover F and G. Now see what are left. A, B, C is left out. Only C vertex is left out. So now it's your choice. You take either E3 or E4. If you take E3, you will get 1. If you take E4, you will get another.
Yes, sir.
So I think you have got the algorithm. That is very simple. Take snapshot. I will jump to the next slide. So
And the
this is what
previous
I
slide
have
also.
written. Okay, okay, yeah. So here also I have said this thing, na, include edges in such a way that two new vertices are covered by every edge, and in last include edges which are covered one new vertex and stop when all vertices are covered.
Yes, sir.
Take snapshot.
Done, sir.
So here also please take.
Sir.
Now how to check cover is minimal or not? So for that we have a theorem. So a cover is minimal if and only if every component of cover is a star graph. That means star graph is K1n. That means complete graph where here one and here n vertices like this. So K11 is this, K12 is this. So here one vertex and here two vertices. Okay, K13 is just like this, K14 is just like this, K15 will be like this, and so on. So every component look like a star graph. Okay, so only then we will say cover is minimal. Okay, yes. So for example, if I take a cover like this, so the what we have taken previously, E1, E5, E8, E3. So E1, E5, E8, E3. Okay, so here itself I will tell you, don't worry. So you have taken snapshot now.
Sir, I've taken.
Yeah, so here I will tell you E1, E5, E8 and E3. So now see this. So how this look like? This look like this K12. How this look like? K11. How this look like? K11. So every component is just like a star graph, like this. These are the three components. This is the what this theorem is saying. Okay.
Sir.
Yeah. So
Once
take
again,
snapshot
previous.
of this.
Done, sir.
Okay. Now take snapshot of this.
Done, sir.
Okay. So cover is minimal if and only if every component is complete graph. No. Every component is bipartite graph. No. Every component is star graph. Yes. D is wrong. If and only if. Both ways. So I will take C. I have just shown you. This is the theorem which I have told you, no? How to check cover. So a cover is minimal if and only if every component of cover is star graph. So every component is
Yes.
star graph. Okay. Take snapshot. I will jump to the next slide.
Copy, sir.
Okay. So summary. In summary, I will say independent set is just like your matching. Matching was with edges, independent set was with vertices, dominating set was with vertices, but cover is with edges. So one and the same thing, one with vertices, one with edges. So independence number and domination number for a graph are unique and are related to number of vertices. I have told you. Okay, previously we have studied matching number and covering number for a graph are unique and they are related to number of edges. So matching number and covering number is related to edges. Independence number and domination number is related to vertices.
What is it?
Okay, yeah. Take snapshot. I will jump to the next slide.
Done, sir.
Done. Okay.
Sir.
So yeah. So next is perfect matching. What is perfect matching? Matching which is also a covering, that is known as perfect matching. Okay, so for example here we have a graph. Okay, so set E1, E5, E8. So is it a matching? E1, E5, E8? E1, E5, E8. Yes, it is a matching. Why it is matching? Because no adjacent edges we have taken. Matching means no adjacent edges. So no adjacent edges we have taken. So clearly it is matching. Is it covering? So E1 is covering A and B. You have covered D and D. You have covered F and C is not yet covered. So it is not a covering. So E1, E5, E4, E8. Is it matching? E1, E5, E1, E5, E4 and E8. E4. The moment you have taken E4, E5 and E4 are adjacent, but it is not a matching.
But it
Yes,
is covering.
yes, very good. It is a covering. Yes. So perfect matching means matching which is also a covering. So here we have not got any perfect matching. And anyway, if you even try to find it, you will never find it, because in the next slide I will show you a very beautiful theorem. That theorem will clarify your doubt. But here I will say there is no perfect matching here for this graph. What about this? See this graph. Okay. Yeah. Now see this. So E1 and E3. E1 and E3. Is it matching? Yes. Is it covering? Yes. It is
Yes.
covering all the vertices. E2, E4. Is it matching? Yes.
Yes.
It is covering? Yes. So we have
Then it
got
is a
perfect.
perfect.
Okay. Yes.
Yes.
So okay. So now see this. I have written pick non-adjacent edges in such a way that all vertices are covered. That is the way to find the perfect matching. So you will pick non-adjacent edges. Do not pick adjacent edges, but you have to pick them in such a way that all the vertices are covered. Okay, so since you are picking non-adjacent vertices, you are picking non-adjacent edges, that's why it will be matching. Now since we are covering all the vertices, that's why it will be covering. So matching which is covering, that is perfect matching. Okay,
Yes, sir.
yeah. So you can take snapshot. No, everything is not on one slide. Yeah, now it is on one slide. Take snapshot. I will jump to the next slide.
Done, done, sir.
Okay. So theorem is coming. Perfect matching. That is number of vertices are even, one way theorem. I have told you now that I will tell you a theorem. So theorem is saying if we have a perfect matching, the number of vertices should be even. With odd vertices, we can never have a perfect matching. Why?
Yes.
Because if you take odd vertices like this, by common sense, you will say you take AB and you take CD. So AB are covered, CD are covered. Now for to cover E, you either have to take ED or BD. So if the moment you take EB or ED, your matching property will be disturbed. Okay.
Yes, sir.
If you take ED, then obviously it is not a matching. If you take BD, it is not a matching. And if you take AB and CD, it is not a covering. Why it is not a covering? Because two vertices you can cover only four vertices. Sorry, with two edges you can cover only four vertices. What about fifth vertex? Okay, so that's why I have told you perfect matching means number of vertices are even. This is one way theorem. Now see the beauty of logic. P implies Q. Q implies P is clearly wrong. When number of vertices are even, we will have a perfect matching. No, it is not guaranteed. Like number of vertices are even. Very simple as simplest example. See this. How you will cover it? It is non-adjacent. Rather, it is an isolated vertex. You can never cover it. So there are four vertices here, but there is no perfect matching here. Okay. So Q implies P is wrong. Converse is wrong. Okay, inverse not P implies not Q, clearly it is wrong. Same example you can take. Okay, not Q implies not P, that is true because it is contrapositive. Number of so contra not Q means number of vertices are odd, then there will be no perfect matching. That is what exactly we have. I have told you here that there will be no perfect matching here because number of vertices are odd here. Okay, so for this theorem I have taken the contrapositive version. Contrapositive version, that means equivalence version will be number of vertices odd implies no perfect matching. Okay.
Yes, sir.
Take snapshot. I will jump to the next slide.
Done, sir.
Okay. So proof I think I have just given you, but let me read it. Since it is a matching, so no edge must touch each other. Because if edges are touching each other, then obviously it is not a matching. Since it is a covering, so every vertex must be covered. Hence, we need even number of vertices because if number of vertices are odd, then at least one edge will touch other edge in order to cover the last vertex. Okay, so we will cover all the even vertices, but one last vertex will be left out, and to cover that vertex, one edge will touch each other like this.
Huh.
So,
Done, sir.
yeah. So if you
Clear.
take this or this, it will create problem for us. So this is the proof. Take snapshot. I will jump to the next slide.
Done, sir.
Okay. So this is a very beautiful note. So there is no formula to calculate number of perfect matching, but in two special graph we have a formula that is for Cn and Kn. Okay, so I will tell you that formula in the next slide. But there is no formula to calculate number of perfect matching. Okay, whether we have a perfect matching or not, we can check that out. But to find number of perfect matching, there is no formula. Okay, so but for Cn and Kn, we have that formula, and I will tell you in the next slide. Take snapshot.
Done, sir.
Okay. So for Cn, if n is odd, then number of perfect matching is 0. Obviously, when n is odd, no perfect matching. I have told you. See this. Number of vertices are odd, then no perfect matching. So if we have a cycle graph, so for example C5 you take, there will be no perfect matching. C3 you take, no perfect matching, and so on. If n is even, the number of perfect matching will be 2. You can check that out. For example, here number of perfect matching E1 E3, that is perfect matching number 1, and next will be E2 E4. Similarly here you can take, you just pick non-adjacent E1 E3, E1 E3 and E5, or you take E2 E4 E6. Okay,
Yes,
they
sir.
are perfect matching for sure. Okay, so why they are eligible for perfect matching? I have taken 3 edges, so directly and indirectly 6 vertices will be covered. Okay, and there are 6 vertices only.
Yeah.
Covering it is okay, and they and no edges touching each other, so no problem. Okay, so if n is
Done,
even,
sir.
number of perfect matching is 2. Take snapshot. I will jump to the next slide.
Yeah, sir. Done, sir.
Okay, so number of perfect matching for C200 only 2, no problem, because it is even. If it
Yes,
is
sir.
odd, if I say C115, you will say 0.
Yes, sir.
Hmm. Can I jump to the next slide?
Done, sir.
Yeah, so okay, I have written here 1050. Okay, done.
Yes, sir. Uh,
Size of perfect matching, that is number of edges in perfect matching for Cn if n is even. So what will be the size of perfect matching if number of edges in perfect matching? Size of perfect match. Okay, that is size of perfect matching, that is number of edges in perfect matching Cn if n is
for
even.
sure.
So it will be n by 2. Okay, half edges you have to take now. For example, you take C4.
Yes, sir. Yes, sir.
So half edges you have to take now. So because if you take 2 edges, all the 4 vertices will be covered, because one edge, 2 vertices will be covered. Why n by 2? Because one edge cover 2 vertices. Okay, so n by 2 is my answer. Do not say ceiling or floor, because we have taken already n to be even. If n is odd,
Ah,
then we will say 0. No perfect matching. Okay, so you have to remember size of perfect matching. Size of perfect matching means number of edges in it. Okay,
yes, sir.
take snapshot. I will jump to the next slide.
Done, sir.
Hmm. So number of perfect matching of and size of perfect matching for C50. So number of perfect matching will be only 2. Size of perfect matching will be 50 by 2, that is 25. Any doubt?
No, sir.
Okay, take snapshot.
Done, sir.
Okay, next Kn. So number of perfect matching if n is odd is 0, that is for sure. If you take K3, K5, that is for sure it will be 0. But number of perfect matching if n is even, for that we have this formula. So how we have got this formula? So the we have used UOP, unordered partition. So say for example we have taken say K4. Okay, so K4 we have taken. So what you will say, 4 factorial. 4 factorial means you can arrange them in 4 factorial ways, A, B, C, D. You can arrange them in 4 factorial ways. Now divided by 2. Uh, okay, so 2 power. mm,
Done.
okay. So let me tell you that thing. So it will take more time. I should say like this. If we have n vertices in complete graph, so I will divide them, divide this n of size 2 to each. Okay, so 2 vertices I will take, because if you take n into vertices, there will be an edge between them. So I will take 2 vertices each. Okay, so how many groups you will make? N by 2 groups you will make. Okay, are you getting it or not?
I'm getting it, sir.
Okay, so we have n vertices. So we will make group of two vertices each, because you take any two vertices, there will be an edge, because it is a complete graph of n vertices. You pick any two vertices, there will be an edge. So you just make pair of vertices. So two vertices you pick them. So how many pairs you can make from this n? You will make n by 2 pairs.
And
So
by two
directly
pairs. Yes, sir.
I will say like this only. So I want to divide n into n by 2 groups of 2 each. Okay, and it is UOP, unordered partition, because you take here AB, you take here CD, or you swap them. No need to worry, because I'm not labeling these groups. Okay, so I will say n factorial. In UOP we have done it, na? So if you have 4 twice, you want to divide, you want to give, you want to make 2 groups of 2 each. So what will be your answer? 4 factorial divided by 2 factorial, 2 factorial into 2 factorial. Okay, why into 2
Yes,
factorial?
correct.
Because 2 factorial is repeated 2 times. So same is the scenario
Yes,
here.
sir.
2 factorial is 2 only. So that's why I will say 2. Now 2 into 2 into 2, how many times you have to do? And by 2 times you have to do. Okay. So and multiplied by n by 2 factorial. Why n by 2
Yes, sir.
factorial?
Correct.
Because this is repeated n by 2 times. Na? That's why n by 2 factorial divided. So finally what we will get? N factorial divided by 2 power n by 2, because 2 into 2 into 2, n by 2 times. So that means 2 power n by 2, and this 2 is repeated n by 2 times. That's why we have to divide it by n by 2 factorial. Any doubt?
Yes, sir. No, no.
Okay, so by UOP we have got it. So number of perfect matching if n is even is this only. Now since
Hmm.
n is even, so we can take it as 2n also, and now our formula will be, so this is n by 2 is creating problems sometimes. Rather n by 2, n by 2 here also, so some students might confuse. That's why I have taken, we can take it as 2n also. So n replaced by 2n, we will get 2n factorial divided by 2 power n into n factorial. That is my answer. Okay, so for example, if I take n to be 6. Okay, so if I want to find k6, okay, for k6, or okay, let me take a big number, say k10. For k10, how many perfect matching? What will be your answer? You will say 10 factorial divided by 2 power 5 into 5 factorial. From this formula I have taken. So n to be 2n
Hmm.
I am taking na. So 2n is 10. So n will be 5. So 10 factorial divided by 2 power 5 into 5 factorial. And this is very easy from this formula. From this formula also you can take directly 10 2 power 10 by 2, that is 5 into 5 factorial. That is very simple. But still, so in case they might ask this formula, that's why I have given you this. No need to by heart, no need to worry about it. This is your good formula. You can apply it and get your answer in GATE exam. Okay.
Okay, sir.
Yeah,
Okay.
please take snapshot. I will jump to the next slide.
Done.
Okay. So number of perfect matching for K6. This is GATE question. So for K6, what I will say, 6 factorial divided by 2 power 3 into 3 factorial. So 6 factorial, 6 into 5 into 4 into 3 into 2 divided by 2 into 2 into 2 into 3 into 2. Okay, so 2 and 2 got cancelled, 3 and 3 got cancelled, this and this got cancelled. So 2, 3, so 15 is my answer. So number of perfect matching for K6 is 15. This is your GATE question. Okay,
Hmm.
so what is the formula? Formula is n factorial divided by 2 power n by 2 multiplied by n by 2 factorial. No need to by heart this formula, you will forget it. Just try to remember the proof how we have got it. N factorial divided by 2 to 2 to 2 n by 2 terms, that means 2 power n by 2, and because of UOP, unordered partition, 2 to 2 is repeated n by 2 times. That's why I have to divide by n by 2 factorial.
Understood, sir.
Okay, take snapshot. I will jump to the next slide.
Done, sir.
Okay, so number of perfect matching for K and N for a complete graph, complete bipartite graph having n and n vertices. So what will be the number of perfect matching for it? That will be clearly n factorial. How n factorial? See this. If we have say n and n same na, so here 3 and here also 3. So here you can take this. Okay, so this is the complete graph, complete bipartite graph of n and n here. Okay, so number of perfect matching will be n factorial y. You can take this edge, then after taking this, okay, so at first place you have three choices. Let me label this 1, 2 and 3. At first place you have three choices. Okay, and
Yes.
because it will cover either this or this. So now if you take this, so now if you have taken this, then you cannot take this now. So now you are left with two choices. Are you getting it? Let me
Sir.
use
Every
another
time.
color. 1, 2 and 3. These are the three edges. So if you have taken this red edge, now you cannot take this blue edge. Now you have to take either these two edges. And in the last, if you have taken this, then you have to take this green edge only. So into 1. So that means 3 into 2 into 1, that means 6. So clearly for k and n factorial is the answer. That means for first vertex, if you take, you have n choices.
Yes.
N choices. For the next, you have n minus 1 choices. And the next, n minus 2 choices. And so on. N factorial is the answer. Okay.
Sir.
Okay, so that's it. We have completed our discrete mathematics here. So if you have
Okay.
any doubt, you can ask, or if you want me to give proof of something which we have skipped, we can prove that, because we have
No, sir. I need
still.
to go through these things.
Okay, okay, yes, it's good. You should go through it, and if you have any doubt, you can ask me. Okay.
No, sir.
Okay then. So we will wind up the class here itself. That's it. So we have completed it. Okay. Yeah.
So you will be
So
taking the other subjects also
yeah, now we
in the
will
next
take
class.
another subject like CN we are doing. So now I think I will start OS or something, DBMS. Any one of them I will start according to sir.
Rest of all the subjects, rest of all the things you are going to take, sir.
I do not know about that. Sir has said that I will take most probably OS or DBMS. DBMS. One of these two subjects I will take from the next class itself, and
Sir.
then accordingly what he will say, then I will take the subjects. Okay.
Okay, sir. Thank you, sir. Sir.
Okay then. Bye bye. Good night.
Good night, sir.
Okay.